Okay, it's a great pleasure to introduce our next speaker, Nando De Freitas, who will be talking to us about reinforcement learning. So Nando was born in Zimbabwe and spent his childhood in Portugal and Venezuela. And I strongly suggest you read his bio on the Khipu website because it's quite inspiring. He moved to South Africa, where he studied his bachelor's in electronic engineering and his master's in the University of Witwatersrand. And he obtained his PhD from the University of Cambridge in Trinity College. After that, he went on to do a postdoc in artificial intelligence at UC Berkeley, and he became a professor at University of British Columbia, Canada in 2001, and subsequently at the University of Oxford in the UK in 2013. In 2017, he joined DeepMind full-time as a principal scientist to help with the vision of solving intelligence so that future generations can have a better life. And he's also a senior fellow of the Canadian Institute for Advanced Research and has been a recipient of several academic awards. And I just want to highlight this point where it says that he is a scientist to solve intelligence so that future generations can have a better life. So Nando is a big protagonist of change in the machine learning and AI community. So he's been heavily involved with the Indaba, and I think the Indaba actually started thanks to him. And of course, he's a great supporter of Khipu as well. So Nando was at the first Indaba, but I remember before that, in the NeurIPS, before the Indaba happened, Nando tweeted, "NeurIPS, 8,000 people, where are the Africans?" And it was through then that this initiative started of having the deep learning Indaba, and I think really spreading different communities and increasing participation in different communities as well. So I'm really excited to hear about reinforcement learning, but thank you for everything you've done.
Thank you so much. Thank you. Very kind, Danielle. Thank you very much. How's the sound at the back? Over there? Fine. Wow, I've never been so happy to give away the first 10 minutes of my lecture. That was amazing, learning how a Khipu works and how we get abstraction still grounded, being able to get numbers. Very similar to what the Greeks did and Chinese and so on, how they constructed the first number systems, which tended to be bounded. And I'm going to come to that in my talk later. First, I want to do a few quick thanks. First, I want to thank Uruguay. I'm a Canadian scientist. That's why I belong to CIFAR. And I want to thank you, Uruguay, for giving me a visa to attend your country. As a scientist, it would be wonderful if every country gave us visas for us to attend scientific events. We do this for the benefit of humankind, and it's in the best interest of humankind to enable scientists to travel across artificial borders. A Khipu is a good example, a good analogy to AI. A Khipu is a tool that extends our cognitive abilities. And that's precisely what AI is, or this laptop that I'm using to present here. It's a tool that allows us to do more, to achieve more. And of course, in achieving more, you can achieve more good things or achieve worse things. And it's important that we maintain this dialogue where we are attempting to achieve better things. I think AI, the biggest revolution in AI over the last few years, it's really been how a field that was only understood by about 1,000 people, if you wind the clock back 5, 10 years ago, all of a sudden is one that about 1 billion people are talking about on the internet. So that rapid progress has been mind-blowing. It's the thing that surprises me the most. And with this very rapid growth, we need to sort of, I was happy to see Joshua before and so on, thinking a little bit about the impact of what we do. And so we need to continue doing this. But it's inevitable that we will develop AI or AI tools. Machines are as intelligent as any human. There's plenty of proof here that that's possible because it's just a question of replicating some hardware that exists now biologically. It's also essential. This might sound outlandish, but our planet has a limit. And that limit is, how long, if you want to put an upper bound, is how long the sun will exist. And if we don't learn to venture into space, future generations will be doomed. And so they're going to look back at us for what we have done. And the same is in terms of protecting the planet and so on. I love the one example of here in South America, La Isla de la Pascua, what's it called in Easter Island, where you go back there and you see all those faces, and the population disappeared, and they chopped all the trees and so on. So that's a society that lacked imagination and lacked AI, shall we say, in commas, because they could have built boats, they could have moved out. Instead, they built faces that all look the same. They were lacking creativity and so on. AI is hopefully, when we finally make more substantial progress, a way of getting more creativity, more creative ideas that will allow us to attack some of the most fundamental problems this world faces, which includes the things that are within reach, like economic problems, problems of governance, problems of managing health, environment, global warming, and so on, and eventually venture into space. So that's why we do it, because as a scientist, this is an inevitable thing to work on, and it's, I think, one of the most important things to work on. In particular, I work in this area of machine learning, and so let me tell you a little bit about, actually, I wanted to thank a few other people, actually, before I continue, sorry. I want to thank, in particular, all these people who helped me prepare these slides. So a lot of the slides here were prepared by, Bobak, Chaler, David Silva provided me some content, Ferial, who's here in the audience, Ksenia gave me a lot of slides for the end, Mark Belmar, Matt Hoffman, Tom Lepane, and Tom Shaw. And especially thanks to Bobak with some coding exercises and some slides that have some code. He's been working throughout the weekend and so on to deliver those. And Ferial's also been working here extra hours to make sure I would have more presentable slides than what I had originally. I also want to thank the organizers, again, for the opportunity for me to be here. The organizers, I can tell you, and it's my experience with Indaba, they work all year round on this. And it's a second job for them because they also have to do research and so on. So they end up doing horrendous hours of work to make sure that this event happens. But at the same time, I want to ask you to consider volunteering to organize. This is the first Khipu. You will be the future organizers in your countries of hopefully the Khipu X, as we've done with Indaba X, or the next future Khipus. It's important that you volunteer to do this. It's much more important to organize an event like this than to put a few papers on archive. You'll have far more impact in the field of AI by doing this than the impact that you will have by putting a few papers. Thousands of papers get put up every day, and thank you. No. It will be me applauding you very soon, I hope. Okay, so machine learning. To put it in context, it has an inductive component, which is the one that we tend to emphasize, which is learning knowledge by interacting, by observing the world. So you observe and you gain new knowledge. You learn the parameters of a neural network, say in supervised learning or an unsupervised learning, or one of these categories of learning. And of course, that learning is subject to the laws of physics. You can't, in the laws of information, the speed of light and so on. But we don't just observe passively. If I ask you, observe, very soon you will ask me, observe what? or something like that. And that's because we actually use the knowledge that we have to guide what we observe. We do experiments in the world. Babies do this. We're born with the hardware to do that, with the instinct to do that, and so on. Much of RL is about this. It's not just about using observations, but it's about intervening in the world to gain knowledge, and thinking about how to intervene in the world to gain knowledge. However, I want to add that there's also a fundamental problem, which is how do we actually use the knowledge that we have gained to derive new knowledge? This continues being one of the big challenges in AI, and one that we still, I think, haven't addressed quite successfully. So in particular, we can build knowledge like, force is mass times the rate of change of momentum, and then we can find that knowledge was false, and we come up with new laws that involve relativity, and then that knowledge is found to be false again, and we keep creating new theories. The best you can hope is that your theory will work well in a specialized case. I think Einstein said that once. That process of creating new knowledge, that process of being able to talk about infinity, so going back to the Khipu, like going beyond the sort of finite abstraction to the infinite, being able to talk about black holes, as we saw in one of the posters yesterday here. That kind of abstraction we don't have yet, so that remains a challenge. And so we do have associative knowledge, which is about correlation, but the type of explanatory knowledge, causal knowledge, think of it like Newton's laws and so on, they have some explanatory power. That still remains a challenge, but I think it's something for which RL can be a tool to get us closer. And that's why I think RL is interesting as a scientific topic. And you will definitely see less practical applications of RL in what I'm going to present, but I think that's just a matter of time. We're developing the technology as we go. So the biggest successes have been association successes, or simple prediction, supervised learning successes. And there's a magic recipe that has been tried since 2012 that's been successful, and it involves the following ingredients. One is data. And data does not come to you. You build the data set. If you want to really have impact, you build a data set. And you build as big a data set as you can. Because with data, and curating data, I think Danielle made this point earlier today, curating data, getting the right data is extremely hard. This is one of the big open problems, in fact, is how to automatically collect good large data sets. It's easy to collect data sets that are useless, but collecting good ones where we can actually solve problems is challenging. The other thing is we use a big net. Make them as big as you can, and that's kind of been what we've been pushing for. There are some biases, though, like Cho presented his idea of using, for example, skip connections and gating and so on, attention, and those biases are important. And they're fairly broad, fairly universal. You can use them whether you're doing speech or medical records. So it's important to, when you craft your neural network, that you make it general, that you don't make it specific to a particular type of data set. The other measure for success has been that there's always a well-defined goal. Like in speech recognition, it's clear what you're trying to achieve, or in translation, or in image classification. And having a goal is sort of fundamental. So when you do research, I highly recommend you try to always think, what am I trying to achieve now? What am I trying to achieve in 5 years? What do I want to solve? The most important thing is to have a target to solve. And of course, I wrote here, capitalize on the best sort of infrastructure in terms of communication between machines, hardware, and so on. But what do you think is the greatest resource in AI in the last 5 years? Okay, someone said it here. 2 people have said it. People. you are the greatest resource. You are the greatest resource of Latin America, actually. Because it's the growth of people, going from the conferences that had a few, I used to attend ICMO when there was like 200-something people. And now it's like, what's the latest? 6,000, 8,000, something like that. And all these people are contributing daily. We're all contributing through a collaborative effort. And the more of us there is as part of this discussion, the more progress we will make. And the more diversity it is, the more we will ensure that what we develop is aligned with the interests of the world population. So let me get a bit more technical now. So this lecture will be about basics of RL. A lot of the audience here are undergrads, and so if you're an expert in RL, sorry, you'll be bored for the next 50 minutes. But it's important to cover the basics. That's kind of always been the tradition of the Indaba. We lecture. We don't just come and present our latest results. And so that will involve defining what's RL, how does it work, what's a basic algorithm in RL, the policy gradients, and there's a practical after, so you will get to implement your first policy gradient, or for those of you who are new to this. Then there's another important derivation in RL, which is dynamic programming. I'm going to cover that, and that will allow us to talk about DQN, or deep Q networks, which was one of my company's first successes. And I'll talk about something that's very interesting, distribution RL, because I think it's a topic that we don't understand very well, and I think it's good for people here looking for something to work on. Then I will focus on talking about 3 agents that are routinely used by people to solve problems. RL is very broad. I could go on talking to meta-learning and model-based learning and so on. I think a few people will talk about it in the next few days. I'm going to focus just on the basic sort of model-free methods that are used most widely. So how many of you saw the OpenAI hand thing with the, what's it called, the Rubik Cube? So that's PPO. We're going to cover that. R2D3 is basically the latest DQN. And D4PG is a very powerful algorithm for control. That allows you to do things, do RL from data, not just from observations in the world. And finally, I'm going to talk about a few applications. So very quickly, I'll talk about what I've called here Alpha X. Alpha X is like, I guess, the DeepMind brand of Alpha Star and AlphaGo and AlphaZero and so on. And I'll talk about something that I think is the closest to applications, but batch RL. Okay, so RL works as follows. Typically in supervised learning, you have an agent and the agent has observations. But in RL, this agent actually will use those observations to take actions and gather more observations. And by performing actions in the environment is updated, and you get observations, and then you might have internal goals, and you might also get a reward from the environment. You might get to come to the Indaba, and so that's a very rewarding thing. And in a short sentence, this one thanks to Tom Scholl, RL is about making good decisions by learning from experience. Mathematically, I'm going to assume that the environment transitions like this. So these are always for observations. R is for rewards, T is for time, and A is for actions. So given an action in environment and the previous state of the world, you move to a new state of the world relative to the agent. So everything is done in a subjective manner relative to the agent, the observations of the agent. And because the agents obviously only have limited computation and limited ability to observe the world, this will be inherently stochastic. There will be uncertainty, and that's why we use probabilities here. The reward model will also depend on the changes in the environment and the actions that the agent takes. And what the agent controls is this thing that we call a policy. And this policy will be typically, well, in this lecture, will be a neural network. It has some parameters, theta, so these are the parameters of a neural network. This could be an MLP that takes some observation, some image, or a ConvNet that takes some image and outputs a binary decision. And that binary decision changes that will have an impact in the world. In software, I'm going to touch on software to sort of build up for your practical today. We can involve the environment. So in software, we will always have an object called the environment. In Python, you import environment, and typically these will be things like the OpenAI gem, or the DeepMind gem, or many other environments that you'll find in GitHub. And the way you update environment is using this magic command step. Okay, so you will encounter this later today. You load the environment, and you step with an action. So this basically makes the environment update when you're using a simulation. If you're using a robot, it's a different story. Your environment is real life. When you act, you have a policy. The person or the agent is often called an actor, and I will soon say why I'm talking about actors and agents and why it's important to have this distinction. But for now, let's think of the agent as an actor that has a policy, and there's some object here, time step, which basically consists at some time step, it has an observation, and it produces an action. Note that I'm talking about all these object-oriented tools for thinking about RL, and there's a reason for that. There's a crisis of reproducibility in RL. People find it very hard to reproduce an agent that one lab has produced, and I think that largely is a consequence of a lack of good software in reinforcement learning. The equivalent of, say, PyTorch or TensorFlow 2 is still non-existent in the RL world. We will change that soon. So the first thing you're going to do, here's an example of an environment. So an environment could be something like this in Mojoko. And so Mojoko is a physics simulation. So there's gravity, there's a ground plane, and then there's these objects. And here, for example, green means that you achieved the task of balancing these pendulums. And so in code, what we do is we just basically, you download the mcontrol and you just import the controls, the suite of control problems. And so these are typical examples that you can use. And I'm just bringing the DeepMind ones here. In the practical, we'll be using the OpenAI, and just I want you to know that there's actually a lot of environments out there that you can download and try your experiments. These are easy environments because they're fully observable, and what makes this easy is two things. First, you can see everything, but it's even more, because what the machines will see is not just the pixels, which is what you humans are looking at now. No, I use the word humans, people. There's this thing in our community. But you actually, because it's a simulation, you have access to the actual state. So you actually observe exactly what the object is, what the angles are, what the observations. So the input to the policy is the state. And that basically solves the computer vision, which is one of the hardest unsolved problems in AI. So everything is sort of, so you have perfect, you can have perfect information, but you can also do it from pixels. And I will show some examples where we can do things from pixels. The other thing that makes this useful, the other reason why we do simulation, is because we can do this 1,000 times faster than real time in computers. And we can distribute these on the cloud. And so we can learn at a much faster rate. We can sort of move toward, say, evolutionary scales in simulation, but we would not be able to do this in a robot. That's why what people do in robotics always looks simpler because it's much harder to do things when you can't go at 1,000 times real time. So once you import an environment, you can give it a domain, like in this case, for example, in your practical, you will do this card pole thing, which is you move it left and right, and you're trying to balance this pole. And so the task here is to balance. You specify, you have an environment and you have a task. Sorry, you have sort of, yeah, in this case, I use domain as it's a card pole, and the environment consists of the domain where you are and then the task. Now, most of RL works in an episodic way, and it's important to understand this. It's not necessarily the best thing, and a lot of people would like to change this, but this is how it is right now. An episode is a finite amount of experience. So imagine that the agent will act for, say, capital T steps and collect data as part of acting. So it proceeds as follows. An agent will make an observation, and this variable is just here to indicate the episode is not over. You initialize time, and while it's not the end of the episode, you use your policy pi to go from observation to action, so you act. You update the environment, so you update the observations, you update the rewards, you get a reward. And here I'm also using kappa is here to indicate that sometimes you need a variable to indicate that the episode has terminated earlier. For example, if you die in Atari, you can stop there. That's just a detail. You observe the world as before. You can update your policy. You learn from your observations so that the future actions will be influenced. Or you might try to collect data for a while before you update your policy. So you can put some logic here. And this is the episodic loop. This is what you will be doing in your practical. An agent or an actor that acts upon the world usually has this form. It has a policy. It's a structured entity. It has a policy that maps observations to actions in the environment, but it also observes the environment, so it has a method that it's about observing. It may contain internal memory. We often call this replay memory or replay buffers, and it may add observations to this replay. The agent might have a learning method inside, so the method is what basically are the rules that tell the agent how to learn. And so on. So it's a structure object, and if you do it like that, your code is very clean. So your typical code should not look that different than pseudocode. And you should always, I think we didn't go over that, how to write a paper well yesterday, but you should always try to have pseudocode in your papers. Or if you're a very clean coder, you would have pseudocode that kind of looks like your code. So here, this is the same stuff. You reset in the environment, so that's basically set going to the beginning. So this is starting here. And while it's not the end of the episode, you use your policy to produce a new action. You update the environment using the step command that you'll be using today. You observe things in the environment, and then there's a function that would update the parameters of the neural network of the actor. And then you evolve the time and so on. So it's actually implementing the agent acting in an environment is quite easy. This is just an example of how you would go about. I've just included this here for you to look at later when I make the slide available. Now, the reason why we think of actors and agents separately is because I will talk about an agent as being something that can actually have multiple actors. Now, in today's software and hardware infrastructure, it's very easy to distribute your environments in the cloud. That's the power of simulation. Even with robots, you could have several robot arms acting at the same time. But with the typical situations, you distribute in the environment. And so each actor is has its own, say, Atari environment, and it's acting in that environment and collecting observations. And then each actor will throw data into a memory, and then the learner is centralized. It can sort of take data from this memory, and it can update then the policies of the actors. And it can do this in some asynchronous manner and so on. This is a typical modern reinforcement learning agent working at scale. Most of the, it's good to know about this, because most of those impressive agents that you see, like the OpenAI agent, and in fact, all the agents that I'm going to talk about later, they have this distributed manner. But again, if you write your software very carefully, it's possible to use the same software to write the big distributed agents and the single thread agents. Typically, your policy to make decisions will be a neural network. Like this is the example of what it was for Atari. I think of this as like very long time ago, but this is actually just just a few years ago, where Atari looks at an image from pixels, and it had two conv layers with relos and some, I guess, one fully connected layer and a softmax to predict the actions, which is to control a joystick to basically play Atari. Finally, the decisions, you hope to make good decisions. And so we come to the question of defining an objective for the agent. Just like you should have an objective in your research, the agents have an objective. Here begins the controversial bit of RL, which is where do the rewards come from? What should the rewards be? And so there's many ideas on this. Purists would say that the rewards have to be extrinsic. The environment provides us with rewards. And quite often in robotics and so on, what happens is these rewards are hard-coded. And because of that, they're not very general. They're brittle. And there are situations where in robotics where you cannot hard-code. There's a task for which it's nearly impossible to come up with a reward. Things like wanting an animation character, in fact, to walk like, I don't know, Tom Cruise, it's very hard to specify in a mathematical model with a piece of code. But it's something that's easy to get from data. So I think data plays an important role. Intrinsic rewards are basically like the goals of the agent. It could be social, like Natasha Jacques did some work with me on using social influence as an intrinsic reward, and that's actually quite fascinating work, because in a big environment with many agents, she shows how agents learn to be cooperative, to sort of do some task like clean the environment and so on, just by wanting each other to, just by introducing this influence intrinsic motivator. So agents wanting to influence others, they start communicating and so on. And that's sort of important, because in these simulation environments with many agents, by playing with these different types of rewards, we can actually perform like experiments that allows us to understand better things about wealth distribution. Essentially, in the old days, well, we still use game theory to talk about economics and so on. But the models in game theory and in social welfare and so on, they're very simple. They have a lot of assumptions because humans are only so capable at doing good math. And so we ended up using simple linear models and so on when we go and develop these theories. And so we're limited by our capacity. But by using these simulations, we have now a tool to extend, to enlarge what we can do in terms of simulating economies and interactions among agents, to get at things like ethics of how equilibria arise in societies and so on. Imitation, that's like inserting, like, it's a big part of what we do. Once someone does something really well in a community, it would be silly not to copy that. explanation, I have it later, so I'll come to it later, or even language. Language is combinatorial. So the moment we have language, we can specify a combinatorially large set of rewards. So it's very powerful. And it's associated with explanation. So agents might also just like we want to have that one sentence that describes our paper, that one story that's easy to tell, agents should also strive for that. Look for simple explanations, things that are compact, that if you were to vary would break. Quite often people talk about empowerment, which is agents wanting to control. So you can think of like children playing and so on, is trying to, through manipulating the environment and having greater control of an environment, you're learning how objects function and so on. Curiosity. I think a lot of evolution is a race of sensing. From the first creature that sort of saw an advantage of harnessing a protein that would enable it to tell the direction of light, which is basically what leads to trees and so on. They have opsons that allow them to see where the light is so they can grow towards the light. So trees actually do have vision. And of course, we animals have sort of perfected that, but we still use the same basic mechanisms that the trees use. So there's been a race for sensing more, because the more you can sense as an animal, the more of an evolutionary advantage you have. And that's why we also try to sense more, and by building tools again. We build tools like microscopes, we build tools like telescopes, and by building tools like AI, will we increase the ability of what we can sense. It's all about curiosity. Chelsea will probably talk about this tomorrow. Chelsea, where is Chelsea? She's probably finishing her talk for tomorrow. Maximizing your learning progress and so on. So there's many theories out there as how we have intrinsic rewards, and many papers have written on this topic. Okay, let's get into the first thing. Policy gradients. So these are the mathematical objects. To summarize, by an agent interacting with the environment, it gets an episode. An episode consists of a sequence of observations at time 0, time 1, and so on. An agent has a policy. The environment transitions. I've made it Markov here, but we can relax this. You have a reward function, and we're going to talk about another concept that we use is returns. Returns is the sum of all future rewards. So what makes RL special, not like, say, a bandit problem, a supervised learning problem, is that there is a sequence here. The time matters a lot in RL. So it's whenever you have data that's a sequence, there's a chance that RL will be useful. If your data is not of that nature, then a lot of these tools that I'm describing are probably wrong, but first you should see whether you can map your problem to a sequential problem. A lot of problems are sequential. Sometimes the episode doesn't have an end. It goes into the future, infinite. And we introduce a variable between 0 and 1 called a discount factor, so that the immediate rewards have more value than future rewards. And there's debate on whether this is a good idea or not. The main objective of RL is to maximize the expected reward. So over all possible future scenarios, taus, over all possible future trajectories, in expectation, so in probability, we want to maximize our future rewards. Okay? So to do RL, you need to go to Khan Academy, and you need to, if you're observing this and you just get by expectations, do the course on probability and expectation. And then the only other thing you need to know about is gradients and matrices. So those are things you can get in your first and second year of undergrad. Now, this expectation over the trajectories, here the trajectory is stochastic. The environment evolves with this probability model, and then this other probability model gives you the actions. And they're independent. So if you take the product of all of them, that's essentially the expectation. This is the distribution with respect to which this expectation is defined. And what I'm going to do is I'm going to take the product of these probabilities of actions given observations, and I'm going to write it as a single thing. So here, 0 to capital T means A0, A1, A2, A3, all the future A's. So I've just factored it this way so I can do some manipulations more efficiently. This derivation, actually, before I get to the derivation for what I'm going to try to do, so this is basically the objective. I've basically defined all of RL. All of RL is about maximizing this quantity. The next step will be to show how you can maximize it by using a gradient, and that will be using this equation. This is called the policy gradient method. If you know how to compute this gradient, then it's just great stochastic gradient descent. You can solve all sorts of problems. Most of what you've seen about demos of RL, including PPO and so on, they're just doing this. Markov chains have this property that they have a stationary regime. You eventually, over these long sequences, you arrive at a stationary place, at a fixed point. At the fixed point, this holds true. And finally, there is this thing that I'm going to define, a Q function, and then there's this other fundamental equation. In fact, these three equations are related, and there's only one equation, and a few different concepts. But if you know these three equations, you will be able to understand any paper in RL. Because every paper in RL starts with either this equation, or this one, or this one. That's the first equation you will encounter in the paper. And from these equations, different algorithms will be developed. You'll get Impala, A3C, you'll get PPO. From here, you'll get MPO and a few others. You'll get DQN here, you'll get distributional, you get, and so on. All the algorithms come from these three equations. Okay, follow the gradient. So if we take the expectation of the gradient of the expected reward, these first guys don't have any theta, so then the derivative with respect of theta goes straight into the policy. So we're going to differentiate the policy only. And the derivative of a function is the same, the derivative of the log of y is y prime over y. So if you move the y to the other side, you have the derivative of y is y times the derivative of the log. So that's what I've done here. The next thing that I've done is because if you have a probability of many events, and each of these events is independent, and that's what you get by assuming things being Markov, then the probability of the big trajectory is just the product of the individual probabilities. And when you take a log of a product, you get a sum. So we get to this expression. And by the way, I will be here for the rest of the week. So if you want me to go in more detail through any of these derivations, I can go through you. I think it's important to go through them, because once you have them, the rest I think is easy. The rest I think you can do. The rest is all in archive. What did I do here? The next thing is to realize that this whole thing is sort of is something you could sum, and then it will be a constant you could take inside this sum. And so that's what I've done. And I changed the index to Bn just to make things a bit more clear. So I've just moved this inside the sum. The next thing I do is, this is basically now the expectation with respect to this distribution. So I'm going, instead of just having a transition model, I'm going to the full expectation now as a trajectory. So it gets shorter. The other thing is I'm using a trick, which intuitively is a policy at time t will only influence rewards after time t. A policy at time t will not influence the rewards in the past. So this thing then starts at t as opposed to at 0. And that's it. Then the next thing is just to use, this is just a definition of the returns. This is the fundamental equation of policy gradients. Your practical has a long derivation there too, but here it is. So you don't need to go over that in your practical now, so you can go just straight to the coding. So that's the policy gradient. And typically what we do is we collect many episodes in the environment, or many trajectories, say n, and then we approximate the expectation with an average. It turns out that you can use just one at a time as well. So the idea of stochastic gradient. So then your algorithm is basically like this. You compute the returns. There will be a function that's in the practical to compute the returns. Then you will have to, I think, code part of this, how to update the policy. And then you act in the world to generate the trajectory and so on. And that's basically all the practical, all the code that you'll be doing. It will look something like this. You'll build a policy gradient agent that will be also an object that will have things like a policy. It will be able to observe the environment, and it will have a learning algorithm that essentially takes the reward to go, which is the returns times the log of probability, and then you sum, take the average, and that gives you the loss. Once you have the loss using automatic differentiation, you can just get the gradients, and then you apply an optimizer, and boom, you're done. So it's very easy to get to that level. Now, some more concepts. Actually, before I continue, I have until 4:10. Okay, hour 10 minutes. Let me finish with the concepts. We often talk about the state action value function, or the Q function in RL. What's the Q function? The Q function is basically like the expected reward, but we hold the first observation and the first action fixed. So it's given that this is what I'm seeing now, and that this is what I'm doing now, what will be my future? What will be the expected gains in my future? So you hold these fixed to get these. By integrating out the actions, we get the value function, which is, given this current observation, what will be my future? Given that my current observation is O, what will be the values, or what's the expectation of what I will get? And finally, we talk about the advantage function too, which is the Q function minus the expectation of the Q function. So you're basically looking how much better you are doing with respect to the average. And let's try to visualize these things now. And we can do that with a neural network architecture, actually. So this neural network architecture is called a Dueling Network, and it was invented by Ziyu Wang and developed by a few of our colleagues. And what it does is your typical convolutional network, but then it splits into two things, and then we use the mathematical expression before to combine value and advantage to give you Q function. So basically recall that these two are related this way. So Q is equal to V plus A. So here we're going to do the same thing. We're going to add them to get this Q. The advantage of doing it separately is because you can compute all these in a neural network. And the other thing you can do is you can look at, you can compute the derivative of either the value or the advantage function with respect to the input. So we can see how influential different parts of the input in this video will be on the value or the advantage. And I'm going to superimpose that derivative on this image. It's called a saliency. And that essentially shows on the left where the network is attending with respect to value. So what are the valuable things to pay attention to? So and as it's clear, it's valuable to look at where the road is. So when you're driving, you just don't look immediately in front of you. That's a bad sort of newbie driver thing. You try to look at the road ahead, basically. You also look at the scores because in Atari it matters to keep track of the scores. The advantage function will be different. Note that when this car gets close to a car, that's when it needs to pay attention. Because there, it is advantageous to, some actions will be much more advantageous than others. When you're about to crash, some actions will be very critical. And that's when this guy will switch on. By breaking the network this way, and because of that, you're able to learn much more efficiently. And this actually also points out something. A neural network you can insert mathematical expressions in neural networks. And if you have an algorithm and you're missing a step in the algorithm, or you don't know some of the missing steps, you can build a skeleton of the steps that you have, and then you can fill in the other steps. Neural networks essentially implement over many layers algorithms. And the big thing, the revolution that they have, is that in the old days, we had to design the algorithms by hand. The neural networks allow us to learn the algorithms from data. And very complex algorithms. So let's look at the video one more time so you can see. So now it's looking ahead. Let's see this one. When it gets closer to a car, see the light goes on because it's about to crash, so it's important to pay attention. There. And definitely when it crashes, it goes very red because it knows. So that's one possible visualization. There's another thing that you can use to visualize value functions that I find very useful. And this comes to a paper called Nexting. It's a beautiful paper by Joseph Modeo, Adam White, and Rich Sutton. And so they have this robot, I think they call it the critter robot. And what this robot does, it goes around. Okay? And then there's a light somewhere. And so every time it's going around, it sees the light. It has a light sensor. The sensor triggers. And so in green, what you see is basically the sensor triggering. And of course, it's periodic because it's going around in a circle. Now, when you learn a value function for this, and you basically can treat the green as the reward. So you can make this sort of prediction, this temporal prediction be your reward, the light be your reward, although you just have you're going off policy here. And maybe I should make that word clear, off policy. So there are two ways of doing reinforcement learning. I was going to get to it later, but I might as well address it here. One's called on policy, and one's called off policy. The distinction is this, and it's a very important one. On policy learning basically means that when you learn, you gather data with your current policy, and then you update your current policy. In off-policy learning, you can use a different policy to gather data, and a different one to update in the algorithm. So you might be interested in learning a policy using data that was generated by another policy. That's off-policy. It's very useful because one of you can generate data, and now I want to do it. And of course, I probably don't have the same policy as you, but I can use your data to get a better policy for myself. And so when you plot the value functions, they will tend to look like these ideal predictions. So basically, this critter, ahead of time, it starts anticipating what's going to happen. So it's this eerie feeling that you have when you're about to touch and you already know what it's going to feel, what texture it's going to feel, whether it's going to be cold or whether it's going to be warm. That moment, just before we touch anything, we can next it. We can predict what's going to happen. And so it's useful to think of value functions like that as the expectation that you will get when you have rewards that are like these indicator functions. They sort of smooth the reward over time. The other thing you can do with the policy gradient is once you have the action value function, which is basically the expected reward but conditioning on the initial observation and action, you can actually also plug an estimator. If you can guess, and we're going to come to that. That's going to be the other big part. How do we come up with how do we learn Q functions? If we can learn one, you can replace that Q function here. And then you end up with an expected reward that involves the Q function in this. Now, if you put the returns here, the returns is a function of all your future time. So it's the sum of rewards. So you have a lot of variance. Because basically, running an episode is what we call Monte Carlo, is throwing the dice capital T times in a finite horizon. So that's going to have that's going to be unbiased, but it's going to be have a high variance. If you try to learn a neural network to approximate that, it's likely to be biased, but it will reduce the variance. And trading off bias and variance, that is the game that we play. When it comes to policy gradients. Every paper in policy gradients is a different technique for trading off bias and variance, basically. That's one way to think about it. The networks that we use nowadays typically will take an observation, will have many processing layers. This one actually uses a trick by Chelsea as well. She might go into this tomorrow, but this is irrelevant to this talk. What's important is the networks usually have two heads, a Q head and a pi head. And so they're estimating at the same time pi and Q. So to estimate pi, what algorithm do we use? Policy gradients, that's a derivative. That's how we're going to estimate pi. We're going to follow this derivative. So now we just need an algorithm. So you just do stochastic gradient descent. You act in the environment, you collect your data. That enables you to define the loss. You have a network, you take the derivative of the parameters of the network, and you descend in the loss. So that's how we get the pi. And so we update all these parameters of this network. For the Q, we need to define now a loss function to update Q. That's what we're missing. And so basically, this is about, there's two loss functions here, expected reward, and then there's another loss function here. Now, there's a trick. Every time you have an equality, if you have something that involves unknowns on the left and on the right, and you want to find out what they are, you just substitute this equal by a minus, define it as a loss, and you try to minimize that difference. That basically is the game of learning Q functions. That's exactly what DQN does and what a lot of these algorithms will do. How you define the loss turns out to be tricky, and that's why we need a bit more. Oh, here there's another question, another equation, which is the policy gradient. Note that this is over a long trajectory. This is over a product of many probabilities, any Markov probabilities. Now, in the discrete case, a Markov probability is a Markov chain. So a Markov process is a Markov chain. And so the P, the environment update, is just a matrix. Just to assess where you are. What's the largest eigenvalue of a Markov matrix, of a stochastic matrix? For the students. If you have a Markov matrix, the largest eigenvalue is? How many of you ever have studied the PageRank algorithm? Okay, there's a gap in your knowledge. There's a gap in Latin American teaching. Eigenvalues. How many of you studied eigenvalues? Okay. This is the problem. What is an eigenvalue? Can someone define an eigenvalue for me? There's this guy. He was the last one to put a hand down. Correct. So he made a correct statement, which is AX equal lambda x. Okay, everyone know that one? Okay, this is how we remember this. So the matrix, the transformation power of the matrix is the same as, say, the transformation of a single scalar. It's remarkable that there's that equality, isn't it? The matrix, the single scalar has as much power in changing x as the big matrix. This is remarkable. What's an application of it? So let's see, hands up. Someone said stability? Like what kind of stability? Oh, you have it. You could have answered my question then earlier. Yeah, it's 1. So for a stochastic matrix, the largest eigenvalue is 1. And this is the same as the thing that arises in LSTMs. If it's bigger than 1, multiplying it by a matrix means that it's going to keep growing. If that matrix has eigenvalue greater than 1, multiplying by a matrix will keep expanding that vector. It will blow up to infinity. If its eigenvalue is less than 1, it will shrink it to 0. So you need that perfect thing, which is you need a matrix to have one eigenvalue that's 1, and all eigenvalues to be less than 1, at least in absolute value. In education, if there's teachers here to teach the stuff, it's important, and it's very sad that students know that AX equal lambda X, but are not able to come up with hundreds of examples. And this is not the problem of the students. This is a problem of our education system. It's just we have failed as teachers if they don't know this, and they know that AX equal lambda X. Eigenvalues are these magic things. They describe the quantum world. Eigenfunctions are the wave functions. They give us the probabilities of where electrons happen and so on. They're the foundations of how we study proteins and quantum phenomena and so on. In the old days, we used to use something called radio until, actually, I was going to say the internet, but it was actually video that killed the radio song, for those of you who remember that. But a tuner is just basically you're moving the eigenvalue basically until you get the eigenfunction matching the incoming wave's eigenfunction, and then you get a phenomenon called resonance. And it's important to know eigenvalues if you build bridges, because if the steps of the people walking on the bridge have a resonance that is different, sort of have the same wave function as the structural wave function, you will fall through the bridge catastrophically. So there's an algorithm that Google uses. This is what made Google a big company. Eigenvector computation. You can take users, and I'm completely going off topic here, but I think this is important. You take the network of users, and for each person, they solved a concrete, specific problem. They weren't trying to do sort of abstract math and so on, but in doing so, very quickly, there were lots of theorists trying to develop more theory for their algorithm. But what they did was very simple. They just basically looked at how one person, how one website connects to another website and so on, because they wanted to know basically the eigenvector, which is each entry of that vector corresponds to a website, and they wanted to know what is the importance of these different. So they basically ran a Markov chain on this graph, on the web graph. And that algorithm is called PageRank. And it just basically is something we call the power algorithm. So the guys in Brazil doing applied math. How many of you know the power method? Okay, there's a few of you. So Brazil has a big tradition of numerical computing. So you need to add PageRank and power methods and so on to your education. It's very important to get the basics. And it's very important to be able to not just learn something from a book as a mathematical object and so on. Abstraction is important, of course, but it's also important to actually be able to relate that to the world. It's funny because I just finished reading a book of Feynman, and he points out that in his visit to Brazil many years ago, someone could regurgitate a mathematical fact, but could not explain why plastic glows in the dark. And this is a bit like that. So it's important. There's no distinction between pure and applied research. I've said this already before, and I will say it many, many times until I leave on this weekend. And it's by going and solving the applied problems like Google did that you actually advance science significantly, vastly. And so another application of Markov chains is reinforcement learning. And so in reinforcement learning, and if you're not familiar with this, there's this thing called Khan Academy, which sort of is a very good website where you can go and learn about this. Thanks to online resources, these days we can do a lot of this stuff. So it's important to get the basics. It's the basics of probability, the basics of linear algebra, and the basics of calculus. With the basics, deep learning is trivial. But you need to have the basics. So you need to build the basics first and then before you embark on this. I believe that in the future, this kind of basics that we teach is something that high school students will be doing. And deep learning will be a thing for undergrads. And it's because of that that I think this is already the case in a lot of US universities and British universities and so on, where you have the undergrads writing the papers. And so you just need to get the basics right. Okay, having said that, this basic expectation can be thought of a trajectory, can be thought of successive multiplication by a matrix, or by a Markov operator in the continuous case. And that the same theorem that says that you can find an eigenvalue that tells you how important each page is, what Google created, the same theorem can also be used to say that there is a fixed point. And at the fixed point, the important thing is you don't need the whole trajectory, the distribution of a whole trajectory. You just need a distribution called a stationary distribution of the current observation and the current action. So you only have two quantities there, just one A, one O, instead of, in the infinite case, an infinite number of O's and an infinite number of A's. So instead of having to throw an infinite number of dice, you now only need to throw 2 dice. So your variance will be much less. It's really important to use that intuition too. And so we arrive at this equation. And that's basically this. And in the particular case of RL, this is called the policy gradient algorithm, the policy gradient theorem. And it's by these amazing machine learning researchers, Rich Sutton, David McAllister, Satinder Singh, and Yishay Mansour. I highly recommend that paper. It's only 4 pages, I think, but it's the good stuff. And so basically, we can either think of the policy gradient this way or this way. I can, if you're interested, I can go over this derivation in a bit more detail with you outside. Okay, so we need one more thing, the Q function. Quickly, the Q function, the value, just like we did for the Q function, if you hold the first observation fixed, so this is the expectation, and the bar here means given, or given that I am fixing the first one, under a stochastic policy, so we're going to switch the game now a little bit, and this can also be done for, deterministic policy. So instead of a probability now, what I have here now is a deterministic function. Takes the observation, outputs A. So you can have either deterministic or stochastic policies. I'm going to do this derivation now with a deterministic. But everything I've been talking about, you can mix and match. Once you learn to do one, I advise you to go and practice doing it for the other case. We're also going to talk about the optimal value function. Okay, so the optimal value function was if you had the best possible policy, if you had the best possible action plan, how much reward would you get? So the star here is for optimal. Here is under a specific policy. Value functions are always with respect to a policy, or in this case, with respect to the optimal policy. So here comes the second important derivation. If we start with the definition of the value function, we can take the first term, factor the first term out of the sum, so the reward at 0. And then now the sum starts from 1 instead of 0. Now the policy consists of the sequence of actions. So it's your plan of action over the future. The policy will be the sequence of all actions that you will take. It's a rule for how to act. So we're going to take the first one out. And the reason for taking the first one out and the observation is because this term doesn't depend on the future actions or the future observations. And so I can move the max operator inside and the expectation inside. So I'm distributing. So this is basically dynamic programming. Dynamic programming is about, if you want to compute A times B plus A times C, a good way to do that is to first add B plus C and then multiply it times A. So A times, open brackets, B plus C. So distributing sums is basically sums of products, products of sums become sums of products and so on. That's basically dynamic programming. It's one of the most useful ideas in computer science, in the design of algorithms. So after distributing, I'm going to knock down the power of this t by 1, and I'm going to take 1 gamma out. And the reason why I do that is because now this basically here is the value function, but if I was starting at 1 as opposed to starting at 0. So it's the future value function, the value function given that I start at 1. And by doing this, I have defined a fixed point again. And that's this beautiful fixed point, that the optimal value function now And if I use prime to indicate the future observation, to simplify, to get rid of time index, because the beautiful thing about a fixed point is I no longer need to keep the time index because I no longer have a trajectory. I just have now and after. Now and O prime after. And this basically says, if I do the optimal thing in the future and I maximize my immediate reward, that will be the optimal thing to do now. So if I knew what to do at the next time step, so basically if you know what to do, the best thing you could do at the end, at time step t-1, you do the best thing, and at times t-2, you do the best thing. So if you keep going, if you did the best thing at the end and you keep going back, you will still do the best thing overall over the whole trajectory. And that's essentially the essence of this. And this simple equation allows us to do that. Now, because the policy is deterministic, the value function is the expectation of Q. But if we act by picking just a single A, so you have a Dirac mass, so you have an impulse function. So your value function is just the max over the optimal action. So the expectation is at the singleton, so it's the max. And then the value function, so you can replace this max over A for this guy here. And you could also use this definition here. So you replace V naught star by the max of a Q star or A prime, and you get this equation, which is the second important equation. If you don't use the max operator throughout, and you just use a pi, and that's the homework exercise for you, you will get this equation, which is the third fundamental equation. And so we've derived the 3 equations you need to know in order to do RL. So now you can go to any paper, and when you see these 3 equations, you know what they're talking about, how they arrived at the result, because they will never derive this, because this is sort of considered the basic knowledge. But once you're here, you can fast forward now to DeepMind and look at DeepMind's achievements a few years ago. Do you guys want to stand up and stretch or something? Let's do a stretch exercise. Yeah, come on, grab some water, because I still have 40 minutes to go, so.
After no one answered the eigenvalue thing, I started asking around, and some people didn't raise their hand. And I know no one eigenvalues didn't raise their hand, so I'm a little bit relieved. I think it's a bit fear. Yeah, everyone should know the basics. Can you go back to slides?
Oh, that's a typo. That's typo. Yeah, but it wasn't intended. Need to fix that type. We will do that. Before I release the slides, I will update. In the third one, in this one we want it there. Yeah, that one was wrong. Sorry, he also noticed it. I'll fix the typo. Thank you. All right, let's get started again. The break was good. Everybody feeling a bit better, stretched. And good news, I'm told that quite a few of you were just shy and terrorized by me or something. And that's why you didn't voice your opinion on the largest eigenvalue for Markov matrix. So that was refreshing. But don't give in to fear. Fear leads to the dark side. And it's okay to be wrong. And in fact, I'm going to use it's okay to be wrong to admit that I made a typo here. Someone just corrected me. In this last equation, there shouldn't be a max. When I give you the final slides, that typo will be fixed. These equations are correct. OK, so let's go back to this one. And what we're going to do to get deep Q networks, or DQN, of the Atari playing engine of DeepMind, we're just going to use the fact that we have this equality, and then if you have an equality, to minimize that equality, we're going to introduce a loss function. And that's precisely what we get. So the right-hand side was this, and the left-hand side was this, and we're going to try to minimize this difference, and we pick an L2 loss. And now the question is, where does the stationary data come from? So we're going to assume that the agent has a memory, that's a replay buffer. And a lot of the intuition for doing this came from neuroscience. So our CEO, Demis Hassabis, is very interested in the process of memory consolidation in the hippocampus. So how when we sleep at night, our brain works more than when we're awake, and our memories of today get consolidated into permanent memories. And so we have this raw data. And what we do, if we have many tuples, what we do is we have a memory, and in the memory, we store tuples, sets of objects consisting of pairs of observations, actions, and rewards. When the observations are states, this is S, and this is S, and this is often called SARSA. We call the SARSA tuples, and there's also an algorithm called SARSA, which you get from these equations as well. So you sample an observation, or you can sample a mini batch of these, and then you minimize this loss over theta. And the only thing we're going to do, in order to get a stable algorithm, it's important to hold one of these fixed while we update the other one. So every 1,000 steps, you will for 1,000 steps, say, for example, you will be updating this theta. And then after 1,000 steps, then this theta star becomes this theta. So this thing is called the target network. So in DQN, we're going to maintain two networks, this and this one. And the target network defines the target objective that we're doing regression, least squares, well, basically L2 regression. And so we're just going to update this by gradient descent. Okay, there's never, all of deep learning is just basically follow the gradient. All of our RL is the same thing. If you can get this, if you can follow gradients, so tape, and then 2 more lines of code, and you have this. So we take the derivative of the loss that we're optimizing. So it's the differentiating x squared. So you get 2 times the function times the derivative, which is this. This guy doesn't depend on theta I. This is a fixed theta, so we don't take the derivative with respect to that. And of course, the way you choose actions is by maximizing. You choose the action that maximizes your value, your future expected rewards. So that's the policy. It's a deterministic policy in this case. So it's a neural network that, in the discrete case, if you have actions, it basically takes the observation. So if you say in Atari, you'll take 4 or a sequence of video frames, and then you map it to the discrete actions which correspond to the joystick movements. In the continuous case, this might output the mean and the variance of a Gaussian, which is what we use, say, to decide where to move next. That's basically it. So, you can, and that's it. That's what DeepMind put out there. And then this works, and with this you can play Atari, and you can do OpenAI. You can do all sorts of things. So you basically have two basic algorithms that you can implement very easily from the beginning, which is policy gradients and a dynamic programming algorithm, DQN. Now that algorithm has a problem, which is, here we're taking the max of the Q function. This is a detail, but it's a very important detail. When we plot these value functions over time, they tend to be very high variance. So I'm plotting here the confidence intervals. Actually, Ado van Hessel plotted this. And so because of that, when you pick the max, so don't forget you're not working with deterministic algorithms. The policy is deterministic, but these algorithms are still stochastic. The problem with RL that makes it hard to debug and very hard to reproduce and so on is the stochasticity. So when you pick the max of a Q, you will tend to overestimate because you're going to be picking these peaks. So you'll be overconfident, and that's not a good idea. So Ado did this minor detail, which is fundamental, which is instead of maximizing of finding the max Q by choosing the action, he actually, for the current behavior network, he finds the argmax for that, and that's the action that he puts here, and then the theorems are in the paper showing why that's a good thing. In practice, this is essential to get good performance. DQN, again, the code is the same. If you have an actor object, then you will define an update method, which is to change the parameter. So if you have that distributed code that we talked about at the beginning, you're just going to replace the policy gradient by, you just replace one function, the update. And then, anyway, I'm not going to go into this, but this is sort of the target reward plus, the bootstrap algorithm, and then you do the tape as well. When you evaluate the networks, you get the loss. Once you have the loss, you compute the gradients, and then you optimize. And if you do that, you'll get this. You'll get an awesome Atari playing agent from pixels. This was revolutionary at the time. We never knew that we could do RL in such high dimensions. And of course, initially the agent is not so good. After a while, what tends to happen is, let's accelerate it. It gets better and better. And then eventually it starts doing this. It becomes superhuman. I love that game. Things have changed so much over the years. So this was the network that we used for that example. It was a simple 2-layer ConvNet, and it stayed like that for like the first 4 years. This is the evolution of deep learning in just 5 years. The 5 years I've been at DeepMind. When I got there, this is the sort of thing folks were playing with. Ado actually came after me and started doing this double DQN, and then ZU with the dueling and so on. But nowadays, our networks look like this. They're massive networks, just like the massive networks that we use in vision. And I never thought, in fact, I was of the opinion, and I was wrong, that you could never use RL to train such big networks. But the fact is we can. We have learned to control the algorithms to do this. So now we use networks like this, and this one is from one of Chelsea Finn and collaborators, what they use for robotics, also these sort of massive networks. So we have all the equations, but I'm going to do one modification of this equation, because it turns out that there is one thing about this equation. There's one thing we can do that does give us way better results. And it's the following. A DQN network, or deep Q network, basically outputs Q functions. So you take the observation, and then there will be a head for each action. So if you have 4 actions, there will be 4 outputs. And then the largest output, that's the action that you take. And then given that you take, say, action 1, you have a Q value. So you have one single value. You have the mean. The mean is a single value. Enter distribution RL. There, what you do is you output a distribution. So you have way more outputs. So for each of the 4 actions, you also have a discrete grid, in this case 5 bins, where you maintain a histogram of the reward probability. Okay? Oh, the return probability. So instead of just maintaining the mean, you will maintain the full distribution or a discrete approximation of the distribution. You can do it with bins, you can do it with mixtures of Gaussians. And so the action that you take, and so basically, so I should do this first. So basically what this is basically saying that each of these bins, each of these ZIs, they will take, so the output will be one of these values with probability proportional to this. So basically this network implements the function f, and then you do a soft max normalization, so you get a probability. And so you compute these histograms, and instead of taking, so to choose the actions, you still compute the maximum Q, the maximum expected value. Why do we compute the maximum expected value? Why is that a good thing to do for an agent? Why should you maximize your expected returns? Sorry? Yeah, so it goes back to von Neumann and Morgenstern utility theory. It is correctly, okay, most of you know this, that's important. So basically von Neumann and Morgenstern have this famous 1949 book on game theory, where they basically talk about what are rational agents, and they lay out some axioms of preferences that are sort of very hard to, very unassailable. And so according to those axioms, you can derive that the optimal thing for an agent to do is to maximize its expected utility. And then in statistics and so on, there's also a big lot of school, there's a big school of thought behind that with Savage and so on. So an agent maximizes its expected utility, so it's the expectation of the return, so Z here means the returns. So the expectation of Z gives you Q. And the expectation, of course, is approximated as this. It's just a definition of the expectation. So if you can predict these guys and you're maintaining these bins, you can compute the Q function, and then you can compute the action. So when we do the Bellman backup, instead of minimizing the L2 function, what you do is you minimize in distribution the difference between the target and the source. And there's a fairly complicated procedure for doing that, which is illustrated here. And I highly recommend this blog by Massimiliano Tomasoli, which very quickly will teach you how to interpret this equation and how you get these results. But for now, let's look at some cool videos of what it does. And these were the developers of this particular algorithm, C51, Will Dabney, Mark Bellmer, Will Dabney, and Remy Munoz. This is one of the greatest RL researchers, I think, in present. He's come up with all amazing ideas. I mean, they're all fantastic, actually. And so the agent here maintains a whole distribution over the expected returns. You're computing this over time. Why this is important is because when you go to applications that are what we call batch RL, when you're doing RL, but instead of acting in the world, all you do is you sample trajectories from a memory. And that memory might have things that were inserted by other agents. So you, as an agent, are not necessarily acting in the environment. You're just learning from the data in your head, basically. So you're doing the decision-making in your head. RL is about acting in the world. And through acting in the world, it's about performing experiments, trying things, seeing what things you do in exploration. You trade off exploitation to go toward the reward and exploring, because you might find something better somewhere else. And so in a way, you're conducting experiments, and so you're developing causal theories with respect to that reward. When you learn just from data, you can still get causation under specific conditions. I'm not going to go into that topic. I think Daniel already mentioned one of those techniques, like mediation. But that's a fascinating thing that connects causality with off-policy research, and it's a great topic of research. These agents, when you try them in the sort of off-policy setting, they're way better than, the distributional algorithms are way better than non-distributional ones, and especially for these complex games where you do theory of mind like Hanabi and some challenges out there. So distributional algorithm is really something worth learning. And there's a version that uses quantiles that's kind of clean for those of you who are statistically prone, who like quantile regression. I recommend this paper. And it's also described in that blog that I referred to. Okay, we now have all the background. So let's go into agents. What are the good agents out there? One of my favorite agents, D4PG. This is like one of the best things ever. It basically uses the policy gradient theorem. So for the deterministic policy, the policy gradient, so you have a policy that goes from observations to actions, and then you have another network that is a Q network that takes the actions and evaluates the Q functions. This is called an actor. This is called a critic. So the actor sort of does things, acts in the world, and the critic says, given the state of the world and what you did, this is how valuable it is. So it's criticizing what you've done. And so basically what we do is the expected reward is the expectation of your Q function with respect to the stationarity, according to the policy gradient theorem. And then you just take the derivative. And we do differentiation, the chain rules. So it's the derivative with respect to theta. You need to take the derivative, because Q is a function of theta, so it's dq dA times the pi, dA, which is pi times d theta. And if you have the gradients, you have a memory, replay again, you sample a memory, and given the sampled memory, you update, you get the delta, the difference between the target and the source, and then you just basically do dqn. So this equation is just dqn. So you follow the gradient of the Q function using which is this difference times delta Q. And then the other equation is the policy gradient. So again, it's only those three equations. Most algorithms use two of them. D4PG will use the stationary one and the Q function. And like PPO will use the non-stationary one, the other policy gradient, and the Q function. And they just mix and match. And then you can also trivially replace the Q by the expectation of the returns. And if you do that, you get agents where you can actually see, you maintain an expectation of returns. So this guy is running, and it's bumping in the walls gives it negative reward. And as it's approaching the wall, you can see that there's two distributions of rewards. So it knows that as it's as it's seeing a wall, either I'm going to crash or not going to crash. So it's maintaining uncertainty. And because you maintain this bimodality of the two things that could happen, you're much more robust. And this thing can be used for these cool manipulation things with hands too. And it can also be used to train algorithms that are used for imitating. So this is an important trend in reinforcement learning, that we have observations. So we may see someone performing a task, and so if we have that data, we can use that data so we can perform that task. That becomes our reward to imitate. And how can we do this? We use the magic of GANs. So in GANs, you want to generate an image. You basically have a generator that's a convnet or something reversed. You start with noise, and you generate some nice, beautiful images. And then you might have real samples. And then the objective of the discriminator is to tell whether the images are real or fake. This is the same thing. You have an agent interacting with the environment. The agent is producing trajectories, behavior. And then you look at the demonstration behavior. And if the two behaviors are not the same, then the discriminator says that there's an error. And so then the game is the policy tries to fool the discriminator, and then the discriminator makes sure that the policy doesn't fool it. And if they play this game, this adversarial game, you end up with a very nice algorithm for imitating a demonstrator. So this is called generative adversarial learning. And one of the things you can do with D4PG, in fact, Konrad Zollner, Scott Reed, Zi Wang, and a few other colleagues at DeepMind have been using this to design algorithms that sort of in these sort of robotic settings learn to imitate. So Gale doesn't work so well from pixels, it works well from features. When you add confounding things from pixels is learning from pixels is incredibly hard. It's like infinitely harder than learning from observations. It's much more difficult, not just computationally, but real images have all sorts of artifacts that can get you in trouble. But they've managed to stabilize it, and they can do things like the expert might even have different appearance than the actor. So this is called third-person imitation, where, for example, my little daughter imitates me when I walk. She has the same gait, that's the sort of thinking. That was the D4PG. Now, there's a whole family of algorithms that tend to sort of be much more aggressive. Their own policy, they're less about collecting big data sets and storing them in memory, keeping in memory like DQN and D4PG, and instead they just maintain a short queue of data. And they just basically, the data that is used to update the algorithm is the data that is being collected, as opposed to data produced by other agents or data in the past. The beautiful thing about these algorithms is that there are scenarios. Again, now we come to simulation. If you can run simulations thousands of times the speed of real time, and you can run billions of these simulations at the same time, then these algorithms will shine. Things like PPO, Acer, TRPO, Impala. These four, this is basically the same algorithm with engineering differences. And those engineering differences are very critical as well in performance. And then this other one sort of uses MPO, will use, so this one has a probabilistic interpretation. This is maximum probability optimization. This is proximal, this is trust region. This one actually combines some of the aspects of this with memory, with learning of policy. There's no point in me going into these algorithms. These are the equations for all of them that get updated. But they're all the same sort of thing. They're an expectation of the Q function or the advantage function. So this is PPO. This is the thing of OpenAI that they used for data all over and over the time. All of them are distributed algorithms, many actors. Sometimes they have a couple of learners and so on. So it's important that you sort of be aware of the software and distribute it that I mentioned in the beginning so you can understand these papers. So they all will have something like this. In this case, this is the Impala agent of DeepMind. Then you act according to an old policy, and then you need to update a policy. So you maintain for stability, you maintain two policies again. One, that you update one policy every few steps. And because the policy that you're acting on is different than the one you're learning, they do importance sampling. So do you have this importance ratio, for those of you who know importance sampling? So you have a ratio between what you're using to act and what you're actually using to learn. And then what you do, that's very important as well. So those are the two tricks that they always throw in. Importance sampling, and they usually clip it as well. Then the other trick is the current policy should not be too different than the old policy. And a way to measure the difference in distributions is to use the KL divergence, which is just 1p, the log of the ratio of these two other p's. So we can easily get an analytical expression for this. And so you optimize this. And this is a policy gradient algorithm, except that there's a queue in how the data gets pumped. And there's better algorithms to get better estimators of this, like one of them is retrace. That basically gives us Impala. TRPO, again, this is TRPO. It's exactly the same thing, except they're putting the constraint on top as in a Lagrangian. The constraint is made here. Again, you have the ratio. You don't want it to be too far. This was Acer. I'm not even going to go into that. It's the same sort of concept. And then I will talk about, in particular, the one that uses memory MPO. So this is PPO. I mean, it's a huge success story. You're able to do something that had not been achieved till now, which is to actually have control with a robotic hand of doing this sort of fine manipulation. This, by the way, is the hard problem. Solving the cube, that you can do with an algorithm. We know how to do that. That symbolic problem is actually trivial in this case. In general, it's a very hard one, but in this case, it's trivial. And so the hard thing is to learn to manipulate the things we take for granted. And this is what we've learned in vision. In the 60s and so on, 50s, people gave some researcher who's this big professor who had mapped out clearly how to solve AI, thought vision was just a side project. And so wisely, he handed it to the undergrads and told them, please finish this by the end of the summer. We still do that. We still take for granted how hard it is to do this. Like no robot in existence can do this. That's an unsolved problem. The things that are not obvious to us, because humans are terrible at introspecting. In fact, it's like the gorilla thing that we saw before. Our mechanisms are to protect us from introspecting, so that we always believe we know what we're doing, but most of the time we don't. So it's worth keeping in mind, especially when having heated debates. So MPO maintains a memory, a replay, and has a policy that acts in an environment and it stores things. It maintains these two networks, the critic and the policy. They might share a torso as well. And so the objective essentially is, again, it's like in policy gradients, but instead of having Q times the log of pi, the only thing is you take an exponent of Q. Okay, you try to accelerate it to do bigger steps in exponential space. And you have a temperature parameter, which you learn from data. You can use, again, convex programming to give you this one. And you, again, make sure that the stationary policy from which you're behaving is not far from the policy under which you're acting. And here's an example of what an MPO can do. Control the snake here. Finally, R2D3, R2D2 and R2D3. So R2D2, you know what it is. It's not the little guy. It's basically DQN, but with a recurrent neural network. And in fact, that's all they did. They replaced the ConvNet by a recurrent net. And you might think that's not worth a paper. That's so trivial. It's given like how many for loops there is in this code and so on, it's an extremely hard thing to do. And deciding how to initialize the initial state and how to optimize this thing, actually the engineering is an achievement. I mean, building one of these agents is as hard as building any bridge in the world or any building and so on. These are very complex problems. R2D3 adds one more D to R2D2, and the extra D is for demonstrations. The other Ds are distributional and distributed. So you always want distributional and distributed, always. And then the demonstrations is optional. If you have demonstrations, you should make use of it. R stands for recurrent. You should use a recurrent network if you need memory. And then the other R, I can't remember. What's the other R for? Reinforcement, yes. Gosh, this is a reinforcement learning lecture. No, it doesn't use retrace, no. So Impala uses retrace, R2D3 doesn't. Because it's off policy and it's using distributional for the off policy. So this is an important thing. If you're learning from a memory of policy, never do Q learning, never do like DQN, always use distributional. Distribution is way more robust to being off policy, and we don't understand why that is. Mark Belmar has a few papers, a few conjectures, but that's an interesting research problem. If you're looking for one, understanding distributional RL. So very quickly, it's basically, now I'm using it like more, like I'm using this sort of block diagram to describe it, but it's basically DQN. You have a learner, as in DQN. You have many actors with a recurrent neural net, which are basically recurrent neural networks acting on environments. You maintain demonstrations from users solving the problem, and you maintain a database of your own experiences. And then you sample to update the learner updates the actors act in the environment, keep filling in this memory, and then we have smart ways of sampling from this memory. They're smart, but not very smart. So the best thing we know is something called prioritized replay. It's an algorithm of Tom Shaw's, the best thing you can have. But we know it's not optimal. We know there are other things we can do. Sometimes we hide behind to do way better, and so we don't know how to do better than prioritized replay. That's another open problem. So if you want to think about that one and you make progress in prioritized replay, that's going to influence all of RL, all of policy RL. So here is an interesting task that it solves. This one is partially observed in the sense that you're moving in a maze. It needs to find a bat, knock the ball, pick the ball, place it in a sensor, and then some gate opens and it can get an apple. And these apples is how people code reward in these environments. And here we see it doing this sort of thing in practice. Now, these environments, because they're partially observable, and they have variable initial conditions, and they've much longer horizons in time, they make these, they're much harder than the OpenAI or sort of GEM or the DeepMind GEM, which was fully observable and so on. As humans, looking at these videos, we can't tell that. So one of the big issues also with RL, and especially with researchers publishing and so on, is being able to convince reviewers that what this agent is doing is much more complex. And so you can do it by running a bunch of baselines and showing that it's only R2D3 that is able to match human performance. All the other algorithms don't even take off. They're like really good algorithms. They're just down there. Just pure RL. If you don't use demonstrations, they don't take off. Okay, now for the last few minutes, I'm just going to do a whirlwind 8-minute thing on applications. So these are the great applications. One is a single neural network that is capable of playing shogi, chess, and Go. Moreover, it does so well that it can beat any human at any of these. That's AlphaZero. And what AlphaZero does, it does something called self-play. So that's how you get the rewards. So the agent plays against itself. So it takes turns being white or black in this game of chess. At the end, if this is the agent, it gets a reward of 1 or 0. It wins the game or it doesn't win the game. It's fully observable, so it's easy. And the transition model in this case, how the environment is very trivial in chess and in Go. So it has that advantage, whereas in robotics, it's very complex. It's nonlinear, variable, and all that, non-stationary. But it's combinatorial, on the other hand, here, which makes it hard. We humans tend to think of these things as being hard. But the things that we think are easy are the things that are hard. So using the data collected this way, these episodes or games played, it can compute a policy, and it can compute a value network. And then that's essentially what was used. That's basically AlphaGo. If you haven't watched the movie AlphaGo, I highly, she's watched it. Was it good? It's brilliant. It's so good. Because it's not just about the agent. It's really about the people in the game. And it's like that. It's about that person there that is like started at the age of 8 or so playing this game. All their lives was dedicated to this game. Trained morning to, as a child, just like, you know, it's like these kids playing soccer here in Uruguay, I guess. They do this. They were playing that at 10 p.m. and they play all day to become... And then all of a sudden, one day you see that a machine beats you. You were the best, but you're no longer the best. The movie has a lot of these aspects of how people react to it. And I think every AI researcher should watch that movie. I watched it at Indaba with Chol. We went to a theater to watch it last time. We actually showed it at Indaba. We should show it at Khipu next time. So here is another view of it. So with a few colleagues that I met at Indaba, so these are some guys from Tunisia, they went out and they implemented an AlphaZero to solve the Tower of Hanoi puzzle. So this puzzle is hard because it's the classic recursion thing. And so what these alpha agents do is before they act, given the current policy, they expand a tree and they use the value functions to expand that tree. And then they find the most fruitful of these branches in the tree. And this thing is called MCTS. It's like a game tree. You backpropagate and you choose the action that the tree tells you will be the best. Expanding a tree is essentially imagination. You're planning ahead a few steps. You're imagining what's going to happen if you act according to this policy, and then you take a better action than what you had initially. So you don't act according to the neural network. You expand into scenarios, and then you act. And then after you do all this, you take the reward that you get, and you use that reward to update your value function, and the action that you took that you thought was better by imagining than what you had in the policy is used to retrain the policy. And the policy in the value network is what allows you to imagine. So you learn neural networks that allow you to think into the future. And based on what you think in the future, you update these neural networks, and, and based on what happens in the environment. And doing this, you can do, it's really powerful. Being able to think ahead a few steps is very important for reinforcement learning. Oriol is going to talk about StarCraft, right? Okay, so I'm going to skip that. StarCraft, big application of RL, coming soon via Oriol. Batch RL is something that I'm interested in. It's like when you do RL from data. And I'm going to go quickly over an example of learning in the context of a robot, but this is much broader. So the idea is you have a lot of storage of data, and data's trajectories, observations, and actions. And you might have a human that's providing a reward signal. And just from the data and the reward signal, you learn a neural network policy. So you don't need to act. This is very powerful in robotics, because in simulation, you would need, say, 10 to the 10 or 10 to the 15 steps to learn to do something like putting this bottle on top of this phone. Whereas if you run a robot for that long, it's going to break. That hand costs about $100,000 or something like that. So you can't afford to be breaking those devices. An indication of how robotics is much harder, I think it took, someone told me this, so you verified this, but I think it took OpenAI like a month and a team of a few people to solve the problem in simulation. And then they increased the size of the team by like an order of magnitude or so, and it took them a year to do it in the robot. That's the difference in complexity between simulation and the real world. But if we have data about the robot doing things, then we don't need to actually use the robot to learn. We don't need, so the robot can learn from data. That's the magic of batch RL, is that if we have data, we don't need to act. And a lot of things, whenever you encounter historical data where people took action, okay, you have a data set of what happened and what actions were made, then you can use that data to learn a policy, and you can try to improve on that policy so you can act better. So if you have a data, and this applies to a lot of policy out there. That's why I think it's important to learn about this one. So we have some storage. In the context of robotics, we give some demonstrations, and some user can provide some information preferences that gives us a reward function. We learn a reward neural network. And batch RL just means you do Q function up there. For example, for us, it's just distributional Q learning. We just minimize the difference between the target and the source networks. And that's how we learn the neural network from data. We don't need to act in the world. And then after you do this many times, then you can act in the world. So in the context of the robot, this robot has been working for months, and everything the robot does gets stored. And from that data, we can learn a policy. I'm going to go quickly over this. Some user can provide some sketches. This is a detail of how you could learn a reward function. And once you have a reward function, you can label all your historical data with that reward function, even if the data was collected for other targets. That's the beautiful thing about learning a reward function. You can learn policies using all the historical data, and then you can try it on the robot. And this is just showing that over time it gets better. And then the robot then you can try to sort of break the robot from, the task here is to put a green block on top of the red, and even despite sabotage, the robot can do it. And with diverse types of objects, so it's not hard-coded for a specific type of object. It's faster than human, so I'm gonna have to do that again. As you can see, it's much faster on the right than a human teleoperating with a remote control. And of course, it can handle a large variety of objects and so on. So that's machine learning. That's the promise of learning for robotics, that it will give you generalization. The robots that you see in factories, they're hard-coded. And so if the task changes a little bit, they need to do a lot of coding. But if you have a learning solution, that will be robust. So that's why we invest time in this. I think especially will be very important for these applications like self-driving cars are essentially these robots for which we've collected a lot of data. And so we can learn from the data set a better policy for driving without having to execute a policy. This would also be of great value in medicine where you don't want to execute policies, but you have patient data from which you want to learn better policies. And we saw some of that today. Dialogue systems is another application where you can have dialogues and you can learn policies for how to speak from data. Another example is using historical data of cooling, how people operate thermostats and so on, to design better control policies, sometimes having profound impacts and sort of in the cost of data centers. So there's a good potential benefit coming from that. There's a great talk of David Silver on AI principles. It's part of the Indaba, so I'm going to skip it because I'm out of time. And I will just leave you with this, which are research problems for you to attack. Reproducibility in RL, solving long horizon problems, being able to characterize time, like do jumpy planning. Abstraction is still something we haven't done, and universality, which is, say, for example, being able to talk about infinity as opposed to have upper bounded numbers. Policy evaluation without having to try the robot is also an open problem, and how to do better exploration when your data is very deterministic. Understanding distribution RL is an open problem. Doing better prioritize replay and contrasting it with self-imitation is an open problem. And of course, any work on safety of these autonomous systems and make them robust to failure is also a very important problem, because you will never be able to deploy these systems until we have safety guarantees on their performance. Thank you.
Thank you, Nando, for that amazing tutorial on reinforcement learning. Are there any, we have time for a couple of quick questions, or one quick question. Should we take Luciana?
Hello. Oh.
Hi.
So if I understood correctly, you're always discretizing time, right? Time goes at discrete steps. And it seems that the size of the steps may be dependent on what you're doing exactly. And even within the same task, for each action, the correct step may be smaller or larger to make it optimal, in a sense. Is that something that they take into account, or are the steps always as small as you can make them? Okay.
Time.
Yeah, I thought it could be related to that.
It's precisely that.
So it's a open research.
Deciding how to discretize and so on is an important problem. You may in fact get a stable algorithm or not in control depending on how you discretize.
Right. That's what I thought.
And of course, you also want to do this sort of temporal abstraction, not just think in terms of discrete steps, but being able to do this sort of jumpy planning. So there are things like options of Doina Prekap and her colleagues, Max Q of Tom Dietrich. A few hierarchical reinforcement learning algorithms attempt to answer this question. So there's been some progress, and that's led to some good algorithms. But I think it is fair to say that it's still an open problem.
Thanks.
Thank you. That was a very good question.
I have a lot of questions, but I will go with just one specific. And it's related, or almost the same of my question to Joshua Benjo, which is, what is your personal opinion or experience with Richard Sutton's idea of predicting more than rewards? And if it's that, how that is related with what you mentioned of intrinsic rewards?
I think Rich has a very good idea, and I also like Joshua's comment. They're both right. Distribution RL is actually in a way the latest explanation of Mark that he gave to me when he came and stayed at my place in London, was that when you're predicting the whole distribution, you're just not predicting, in fact, the usual expected reward. You still are predicting that, or you're predicting something close to it, like for these Gaussians, you have the median. But you're also predicting all these other things about the tailored distribution. So you can think of those as auxiliary tasks, what people call auxiliary tasks. So they're making predictions about other things that enable you to learn better. A current open problem is to verify whether that theory is right or whether it's something that we should falsify and come up with a different explanation. And the other thing that we need to learn is what to predict. What are the optimal auxiliary tasks? Some auxiliary tasks are very good. And in fact, David Silver points this out. Actually, your question leads to this. One of David Silver's points of philosophy, and I agree with these. This is great advice for students. He says, control the sensory motor stream. You should be able to predict everything your body feels and do these cross-model predictions and so on. So that this sort of thing that I feel that it's going to be hot and so on. And the other thing is just quickly, always have an evaluation metric, a concrete objective function. Make sure that your algorithms are scalable. They should be linear in storage and so on. Make sure that the training and testing environment should be different. You should they should be general. They should transfer. You should learn from the agent's experience. Collect as much experience. Don't ever throw away experience. Keep it, even if it's bad experience. You can learn from bad experiences. Most of the time, this is the most valuable. David likes to optimize end-to-end, like all the deep learning community. This one can be debated by, I know a few people will debate this. Empower the network, I completely agree. This is what I was saying, that networks can implement any algorithm, and you should use neural networks. Control the sensory motor stream we went over. Each value function is a source of knowledge, especially if you're predicting different things using value functions. This is how you're representing knowledge about the world, your sensory motor stream. State is subjective. That's very important. Your internal state of the world, each of us has a different internal state. So if you have a neural network policy with, say, a recurrence variable, that state is not objective. It's not the state of the environment. That's what the agent believes about the environment. And an interesting thing is doing tests, probes, to figure out what does the agent actually know to understand it better. Or asking the agent questions. And finally, there is this question about time. How do you plan ahead, imagine ahead, especially with jumps in time, for any different time scales? That's the sort of thing that you should always, I highly believe in this. David came up with this at Indaba. He needed to give a talk, and he went to his room, I remember, after we went on a hike, and he sort of worked hard, and he prepared his talk. So for researchers, coming to events like this is quite fruitful. You can go back and give back to your organization. So organizations should sponsor these events because it improves the quality of the research being done. And also, for example, how to write a paper, all those slides that we've been producing, they're now being used to generate courses that various organizations use to train their own employees. So what Khipu and Indaba are doing is already shaping the world. So the community is not just in Latin America and Africa, the community is global. It's all of us together.
Okay, let's thank you again, Nando.